Good afternoon. I'm Beijing Dean of School of Computing. Today is my honor to welcome Professor Barbara Liskov, the winner of 2009 Turing Award, and is an MIT Institute professor to give a talk here. And it's a great pleasure as well as an honors for the school. And on behalf of the school, I would like to thank her for taking time to come to Singapore to evaluate the school, as well as taking time to talk to you all. Barbara not only won the Turing Award, she has won many other awards, including 2004 John Newman Awards, and has been a fellow of ACM, Academy of Arts and Sciences, Academy of Engineering, and she was also identified as by the Discover magazine in 2003 as one of the 50 most important women in science by the magazine. So today, I'm sure she is the most important woman in science today. Without further ado, I thought that a Turing Award winner does not need any introduction. Just need to say I'm a Turing Award winner. That is good enough. Okay, now I would like to welcome Barbara to give us the talk. Thank you.
Okay, thanks very much for the introduction. It's a great honor to get the Turing Award, but it comes with a downside, namely you have to give a Turing lecture. So, of course, after I learned that I received the award, I spent a lot of time thinking about what this lecture would be about. And as part of this thought process, I went back and I went back over the state of the system, or the state of the field at the time that I did the early work that was the main reason why I got the award. And I read a lot of the old papers that I had read originally and thought about the work that was going on at that time, and I realized that actually it was really interesting. And not only that, but my current crop of students had no idea what the field was like at the time. So I, in the end, decided to talk about that. Do is figure out. So that's what I'm going to talk about today. I'm going to focus mostly on the early work that led to the invention of abstract data types, which was the main reason why I got the Turing Award. Then I'll talk a bit about CLUE, which is the programming language that my group at MIT invented to explore that idea and what it really meant. I'll talk a little bit about some work I did on type hierarchy, and I'll conclude with a little bit of discussion about where's the field today. So I got my PhD at Stanford. I finished there in 1968, and I actually did my graduate work in AI. And I knew about halfway through my graduate degree that I was not interested in continuing in AI. I really wanted to switch into computer systems. I decided that it would be a good policy to stick with AI until I had my thesis done, because it would be a faster path to finishing. And after all, the point of getting a PhD is so that you can finish the PhD and go on to do the work that having the PhD enables you to do. So I stuck with AI. But as soon as I finished, I switched into computer systems. Now, after I finished at MIT, I actually went to work at a place called the MITRE Corporation. And the MITRE Corporation is a nonprofit company that works mostly on government contracts. So what happens is the government, the federal government in the US, puts out requests for proposals in particular areas where they're interested in having research done. And MITRE, along with many other organizations, will then bid on these proposals offering to do the research. And so I arrived at MITRE as a fresh PhD, and they had gotten a hold of a proposal to do work on what was called microprogramming. Microprogramming was something where the idea was that you had a very primitive machine with a very small instruction set, very low level, and a read-only memory. And you would use the read-only memory to implement a more standard instruction set that would then be used to actually write programs in. Now, one of the odd things about these microprogram machines, I think I have a picture of the one we used on the next slide. This is the Inner Data 3, and it had 16 instructions, is what I remember. Very primitive instructions, 16K words of read-only memory, a paper tape reader, and a console. That was the whole machine. One of the things that's odd in looking back at these machines from today's perspective is that that instruction set was not that different from a RISC instruction set. What was different then was that people were actually writing a lot of code in machine language at the time. Whereas today, of course, you very rarely do that. You write language, you use a higher level language, the compiler translates into the code. And it's very tedious to write programs in the kind of instruction set that this machine provided. So as my first project, I took that machine and I designed an instruction set which was fairly typical for instruction sets at the time. With one exception, I put semaphores into the hardware. Semaphores, the P&V instructions that Dijkstra invented. I had met Dijkstra, I think, around 1969. I was very interested in his ideas, and I thought this would be really nice to have these instructions available as part of the machine language supported by the machine so you could use them in building higher level programs. Now, after I finished that project, the next question was, well, is this architecture that we implemented good for anything? Is it got all the features in it you need? Can you really use it in practice? And so to answer that question, I went on and designed something called the Venus operating system. Now, you have to understand this in the context of the work at the time, because this was very early days for operating systems, and in particular for time-sharing systems. And Venus was a small time-sharing system that supported 16 concurrent users. And as part of doing this project, I was actually doing research in operating systems because it was just that point in time in which people were doing this kind of very early research in what operating systems were like. The choice of an operating system was a really good one, given the instruction set I had developed, because it allowed me to take advantage of the semaphores to do the concurrency control that was needed to support the fact that I had 16 concurrent users, and of course I also had to worry about I/O and doing that concurrently as well. So I built the Venus operating system, and eventually I wrote it up, and it was submitted to SOSP, which is the Top Systems Conference, where it became a prize paper and was the main reason why I ended up with a position at MIT. And I'll get back to that in a minute. But in the meantime, now that project was over, so I had to go on to something else. And what had happened was that the MITRE Corporation had discovered another proposal that they had submitted to that led to my doing work in program methodology. What had happened was the federal government had discovered what they referred to as the software crisis. And what they meant by this was that people were building software systems that they really didn't understand how to build very well. And as a result, these systems came in late, over budget, if in fact they succeeded at all. And actually, if you go back and look at the history of the 70s and 80s, what you see is project after project where the software absolutely failed completely and you had to scrap the system after spending millions of dollars. And this was primarily due to the fact that people really didn't know how to build big software systems. It was also somewhat also exacerbated by the fact that machines were often under specified in the hardware area. Machines were very expensive in those days, and the cost of building software was completely not understood. And so there was a tendency to say, well, we'll save money on the hardware, and we can just make up for it in the software, which can solve all the problems that the hardware sort of presents to them. And this just made the problem worse. Okay, so as a result of this particular research proposal coming into MITRE, I started to work on program methodology. What is this, what can we do to make the software crisis more manageable? And I'm going to now talk about the state of the art in program methodology and what happened in that area. What I first want to point out is that work in programming methodology actually is aimed at two completely, quite separated topics. The first one is, what is the software design process like? How should programs be designed? The second one is, what kind of software structure are you aiming for, so that in the end you have a software system where you can actually understand what it does and reason about its correctness. And I'm going to be talking about papers that address topics in both of these areas. So the first paper I want to talk about, and oh, by the way, I should say that it's really good for you students to read these papers. These are really good papers, and they are classics in the field. And they give you an idea of where our field has come from and what its inner underpinnings are. So the first paper is this very famous paper by Edgar Dijkstra called Go-To Statement Considered Harmful. This was actually not a full-fledged paper. It was in fact a letter to the editors of the communications of the ACM. It was only a couple of pages long. And it was extremely controversial at the time it was written. Now, Dijkstra's arguing here that we should not use go-to statements in our programming languages. And today, this probably seems to you, younger people as something that's not even worth talking about. Because if you look at our modern programming languages, they do not have go-to statements. But at the time, people were really worried about the loss of the go-to statement. And so it's interesting to think about why was this such a controversial topic. One reason was that people felt that Dijkstra was attacking them personally. You know, they say, I write programs, they use go-to statements, and yet they are well-structured programs. And that's true, because the truth is, you can write a good program no matter how lousy the programming language is, if you just apply discipline and good programming practice to the job. Another reason why people were upset is that they were worried that they might not be able to do the things they had to do if they took the go-to statement away. And that was true for the programming languages that were available at the time because they lacked certain structures that we are familiar with. For example, if you don't have an exception mechanism in your programming language, then how do you write your programs to take care of the fact that when something goes wrong, you want to bring that to the attention of the caller without sort of merging it into the normal results? Well, if you could pass a label as an argument to a procedure and then go to that label, if the exception happens, that's a very nice way to simulate an exception mechanism. If you don't have a case statement, then using an array of labels is a good way to simulate a case statement. So people were right to think that maybe the current languages didn't have enough expressive power. What Dijkstra was saying in this paper is really one of the basic statements about our field as a whole. He was saying it's actually not easy to write correct programs. And the reason it's hard is because when you reason about the correctness of a program, you look at the text of the program, which is static. But what you're reasoning about is the execution of the program, and that's dynamic. And there's quite a separation between those two, especially if the program is written not using well-structured control structures. So if it's written using ifs and whiles and recursion, there is a fairly close correlation between the code that you look at and what happens when the program is executed. But if there are go-to statements and they jump all over the place, and people used to talk about programs as being bowls of spaghetti because there were labels and branches all over the code, then it can be arbitrarily difficult to understand what the program does. And Dijkstra made this point by an analogy. He said, supposing you're debugging a program, and you're at a particular point in your program text and there's an error, and you're trying to figure out what went wrong. Well, if it's a well-structured program, then it's relatively easy for you to figure out how did I get to where I am right now, and this is a big step forward in figuring out what went wrong. If it's an ill-structured program, it can be very difficult to understand how you got there, and that makes it very hard to understand what went wrong. Okay, here's another very famous, very good paper. This is by Nicholas Beard, and this is about, Dijkstra's program is really basically about program structure. This one is about program design. And it was one of the very early papers on proposing a top-down design methodology. Now, we know today that program design is a combination of top-down and bottom-up. because no matter how careful you are, the design decisions that you make early on might not be right. You're going to discover that when you get farther down in the design of the implementation, and then you may have to back up and retake some of your decisions. However, I really believe that fundamentally the program design process has to be top-down, because if you don't pay attention to the problem you're trying to solve, then what likelihood is there that in the end the solution will solve that problem as opposed to something else? What Weir proposed in this paper was a methodology where he said, you have this problem to be solved, so what you do is you make a single design decision. This allows you to write what he referred to as an abstract program, which he thought of as writing as a sequence of comments. And when you're convinced that that abstract expression of your solution is adequate, then you select one or more of those statements and you refine them by making a second design decision. You just iterate this process. And the example he used was the 8 queens problem, where the idea is to get queens on different rows and columns so that none of them can attack one another. And the first design decision he made is to approach this column-wise. So the idea is I've got a solution that works for the first n columns. Now I'm going to extend by adding the n plus first column. If I can find a place to place the queen on that column, then I can go forward. Otherwise, I have to backtrack. Okay, here's another very famous and influential paper. This is a paper by Dave Parnas. Actually, Parnas wrote 2 papers on this topic at about the same time, both of them very good. And this is back again, more on the Dijkstra side. This is really about program structure. And what Parnas said in this paper is really very interesting from today's standpoint. He said, programs are built from modules, but we don't really know what these modules are. However, one thing we know about modules is the whole purpose of having modules is to enable us to do separate the reasoning, so that we can think about the correctness of the program module by module, and this way keep the complexity of the reasoning process under control. And in order for that process to work, Parnas said we have to understand how the modules are connected. Basically, he's saying, he has this very famous statement in this paper, the connections between the modules are the assumptions which the modules make about one another. And what he's saying in that statement is it's more than just understanding that you call a procedure and it has these arguments. Because typically modules connect in more complicated ways than that. They might connect through their use of the file system, through their use of global variables, and so forth, and you have to understand all the connections. In other words, you have to have a complete definition of the interface in order to be able to have this separation of reasoning process. I think we have a, okay. No. All right, I'm getting to give up here. Okay, so I read these papers and a bunch of others. And I realized as I was reading them that I had actually invented a methodology for the Venus operating system project. And I had done that in some sense precisely for the reasons that people were talking about in these papers. I was very worried about how we were going to keep the complexity of the software in that system under control. It was actually a very ambitious project for the time, since people didn't understand operating systems very well, and I was building one. And my methodology, so I had invented a methodology just as a sort of a byproduct to keep things under control, and so I decided to write it up. And what I had decided to do in the design of Venus was to use something I referred to as partitioned. So to understand how systems were built at the time, the idea was that you had this big space of global variables that every piece of your program accessed. And then you might have a bunch of procedures, and they would call one another, and they would also communicate through those global variables. And what I decided was global variables are bad, and we're not going to have any. And so I partitioned the universe of global variables, which is sort of like the system state, among what I called partitions, which were regions of code. And each region of code owned a certain subset of those global variables, and the rest of the modules, the partitions, were not allowed to access those hidden global variables. Instead, they had to call operations of the partition that owned them. So I had what I referred to as a multi-partition, multi-operation module with several operations that you would use to interact with it. So I wrote this up, and it was published I showed you on the previous slide. So now it's the spring or winter of 1972. And as I said, I had written up a paper on the Venus operating system. It was a top paper at SOSP. My program chair there was Jerry Salzer, who was a professor at MIT. He invited me to apply to MIT. And I actually applied to a couple other places as well. What actually had happened was, in the United States, when I got my PhD, nobody was interested in having a woman on the faculty. I had no job offers worth considering. Then the United States passed something called Title IX, and which said something about equal affirmative action, equal opportunity. And as a result, the universities got interested in hiring women. So MIT was actually looking to hire women. And Jerry Salzer, as a professor at MIT, was kind of looking, when he saw me, there I was. And so, he invited me to apply to MIT. And as a result, in the fall of 1972, I moved to MIT. And it turned out to be a very good time for me to make that move, because with my work on programming methodology, I had found the problem I really wanted to work on. And I would not have been happy at MITRE any longer, switching from topic to topic as the newest requests for proposals came in. Now I wanted to set my own research agenda. And one of the nice things about being on the faculty is that you can do this. Of course, you might fail, but you have the ability to decide what you're going to work on and sort of control your own fate. So I went to MIT in the fall of 1972, and this is the question I was working on. I wanted to understand how these ideas that were in these papers that I've mentioned, and also in my own paper on multi-operation modules,